for today. So what I did with chapter 42, I split it up into 2 separate lectures. Today and then next class you get part 2. Part 1, we're going to deal with introducing you to whole body organism effects, what can happen to the body as a whole. We've done a lot to talk about what can happen to individual cells, what can happen to individual chromosomes, how we talk about radiation harmfulness in the context of LET, RBE, those kind of things. We've talked about dose response curves, but now we're going to look at how much radiation causes what effect, right? That's what we're trying to get to. There's a few different ways that we figured this stuff out, that the ways we know these numbers, okay? So one would be epidemiology. Epidemiology is the study of disease in populations. It's hard to say what causes a disease, right? So you have less control over variables, right? One variable might be the population's environment. You have no control over their environment, right? And you need large populations to build statistical analysis of diseases occurring within a population. Scientists can get this from medical records, right? Anonymized medical records. Long time periods make tracking difficult. Epidemiology has to be done over long periods of time, right? You can't measure a population's you can't measure a population's disease occurrence over one day, right? You need to measure it over years of time, decades. The other way of doing this is called extrapolation. Taking the results from known data, for example, we know what happens to mice when we do certain things to them, so then we extrapolate. If this happens to mice, and mice are mammals, well, we're mammals, so maybe the same things happen to us. That's extrapolation, okay? Taking results from known data and projecting how it would change at unobserved levels or in different organisms, based on assumptions that conditions and responses above or below the known data will be consistent with known data. Biologically, as they say, this is not always true. The thing I like to always remember is biology is a little tricky, right? Biology is a little complicated. So it's not as cut and dry as we try to make it sound. But it's all to the best of our abilities. Number 3, the other way of doing this is direct experimentation, okay? Now, this is in laboratory settings. The advantage of direct experimentation is you have good control over your variables. A laboratory setting, they can make everything controlled and then make only one variable at a time and then test the effects of that variable. Control groups used for comparison increase the validity to what causes what effect. The disadvantage is it's hard to say exactly what will happen to people when you're not doing the experiments on people, okay? Should we? No, right? We should not be doing the experiments on people, right? There have been whole big problems with experimenting on people in our past, right? You can look up any number of different ways we've gone wrong experimenting on people, and so we don't do that, right? We probably shouldn't even be experimenting on animals as we learn more and more about what animal consciousness and things like that. But I'm not going to get into that. We do this, and then this class is not going to stop any scientists from doing those things, right? But so we need to learn about them, though, right? We need to learn that these are ways that we get our information, right? All this information we're talking about has come from one of these 3 methods, right? Looking at epidemiology within populations, looking at extrapolating from current data, or direct experimentation. So that's how we got all this. Okay, so let's talk about effects to the body as a whole. Okay, these are going to be assuming a whole body radiation exposure. Although you know that most of the time when we take an X-ray, for example, we do only partial body radiation exposures, right? The beam is collimated to a specific spot in the body. The same is true with things like radiation therapy, right? You'll only get, whole body exposures when you do things like whole body CT scanning, certain radiation therapies. So we usually don't do whole body exposures, but these are the effects that happen to whole body due to whole body exposures. And you can put these effects into 2 categories. And you guys, hopefully these terms are not surprising to you at this point. Deterministic effects or stochastic effects. Deterministic effects are those which we know when they happen. We know if I give you this much radiation, this thing will happen. And I know it. If I give it to you, it happens. If I give it to you, it happens, right? I know it's going to happen. I know how much radiation is required to cause the effect. The effect is determined by the dose. The opposite of that is stochastic effects, random. The effects that are stochastic are usually from low levels of radiation exposure, and we can't say what dose causes what effect. We can only say things like, as we increase the dose, the likelihood of the effect increases. So it's all about statistical appearance of some effect. So this talk that I'm going to do for the rest of this class today is going to be all about the deterministic effects, and we'll get into the stochastic effects next time. Deterministic effects. Increase in severity with increasing dose, above a threshold. So the dose response graph that deterministic effects have, yeah.
I'm looking for Sydney.
I don't think she's here today. No. Or Jessica, right? Yeah, she wasn't here either. Yeah, okay. Okay, so this is important, right? Deterministic effects have a threshold. Okay, what's a threshold in the context of dose response? A limit, right? Below the threshold, what happens? Nothing happens, right? So I can give you any amount up to the threshold, and then nothing happens. Yeah, that's important, right? Because now if we know there's a threshold for something to happen, now we know there's a level below which we can say, this is safe, right? Turns out for diagnostic radiation, there is no threshold, but some things do have thresholds, okay? Some effects do have thresholds, okay? Once you reach the threshold, the effect will happen, with high probability, the effect will now happen, okay? You spend enough time in the sun, you will get a sunburn, right? We know roughly how much time you need to spend in the sun. There's a threshold. If you go outside and walk back in, you didn't get a sunburn, right? If you go outside for an hour or whatever, you get a sunburn. So we know there's a threshold, right? It's not no threshold. People don't walk outside and walk back in with a sunburn. Something is very, very wrong with the sun if that happens, right? Okay, so the effects increase in severity with an increasing dose above a threshold dose. There's always a threshold with deterministic doses. That's very important. The effects are considered certain to occur to the exposed individual as long as the threshold has been reached. Deterministic effects are only associated with large doses of radiation. We don't give large doses of radiation in our X-ray rooms. We give small doses of radiation. So the opposite statement is, we don't cause deterministic effects in the X-ray room. We cause stochastic effects. Deterministic effects are nice because we know when they're going to happen. So as long as we stay below the threshold, we don't make it happen. Radiation therapy and C-arm fluoroscopy, angiography, all of these high-level radiation exposures, they are considered large doses and do pass certain thresholds. Deterministic effects from large doses almost always manifest as early effects. An early effect of radiation, which I will get to talk back to, I will talk more about in a little bit. Early effects of radiation are those that manifest within minutes, days, hours, or weeks after exposure. That's an early effect. Late effects take months to years to manifest. Almost all early effects are deterministic. That means the early effects have a threshold. We know when they happen. Examples of early effects include erythema, or reddening of the skin, decreased blood cell counts, epilation or hair loss, fibrosis, which is like depositing of extra fibrous tissue, atrophy, shrinkage of some tissue, sterility, decreased gamete count. These are some of the examples of early effects. Examples of late effects, which are deterministic, in which there's only one, is a cataract of the eye. You don't get cataract for 10 to 15 years after an exposure, and we know what the threshold is for that exposure. So if you get a certain amount of radiation in one small exposure, we know 10 to 15 years later you're going to develop cataract. It's one of the only examples of deterministic effects that are late, that don't manifest within a few hours or days or weeks. Stochastic effects, and just so you have it, we won't talk about these today. Stochastic effects increase in probability with an increasing dose where there is no threshold. So when we talk about stochastic effects, any amount of radiation can make the thing happen, right? Any amount of radiation can cause the right mutation in the right one of your genes to give you cancer, right? Any amount can. One single photon can do it if it's put in the right spot at the right time, yeah? So because of that, there's no threshold, and they are considered an all or nothing phenomenon. You either do or don't get cancer, right? You don't get like a little bit of cancer. You either have cancer or not, right? There's different types of cancer. That's not what I'm trying to get at. I'm trying to get at the fact that you either do or don't develop the effect, right? It is stochastic. It's random, measured statistically within a population. The odds of a particular individual experiencing the effect are small, but as doses go up within a population, more and more people start having that effect. Stochastic effects can occur at low dose levels, such as those encountered in a diagnostic radiography room like we spend a lot of our time in. Late effects of radiation are stochastic. Most are carcinogenic, cancerous, and others are hereditary or genetic. So you either hand down something to your offspring, or you yourself develop some neoplasm. Stochastic effects follow a linear curve, straight line, with no threshold. See you. Okay. So now it's time to discuss these early effects more in detail. Early effects, which have a threshold, are deterministic, are those that manifest within hours, days, or weeks after exposure, whereas late effects are considered those within months or years. An important note, because mutations happen all the time in our body, because damage happens all the time in our body is really good at repairing itself, okay? It can repair roughly 9 out of 10 damaging events, okay? But that 10th event is damaging and doesn't go away and builds up over time. The more of these events that happen, the more damage that accumulates over time. 90% of damage is repairable and permanent, but that leftover damage becomes unrepairable and accumulates. Early effects of radiation are somatic, not genetic. Can someone translate that into English? Okay, so the early effects happen to the body, and what does it mean to say that they're not genetic?
They're not passed down from your parents.
Absolutely, right? They happen to you, not to your offspring, right? That's good. They are deterministic, not stochastic. Let's translate that into English. What does it mean to say an effect is deterministic? Ooh. You guys all came up with the idea at one time. I think I heard Lewis talk first. There is a threshold, right? And once we reach the threshold, the effect definitely happens, right? And below the threshold, the effect definitely does not happen. That's what we mean by deterministic. And contrast that against stochastic, which means random. It either does or doesn't happen. It's hard to say, right? The effects are nonlinear. Let me give you nonlinear. Nonlinear means that once the threshold is reached, the effect happens. But as you increase dose, the effect gets way worse with just a little bit more dose. The effect gets worse quick rather than proportional with the dose. Doubling the dose does much more than double the effect. Doubling the dose might quadruple the effect, which is what's shown here on these sigmoidal graphs. And they have a threshold. We've described thresholds. So let's look at what some of these whole body early effects are. These are the threshold doses. Below these doses, the effect doesn't occur, and above these doses, the effect is certain to occur. At 250 millisieverts to the whole body, we see decreased blood cell counts. What might the patient be at risk for with decreased blood counts? Anemia. So that would be a decrease in what type of blood cell? Red cells, yeah. So anemia, decrease in red cells. What are some other type of cells that we don't want to lose? Leukocytes, right? White cells, which do the job of fighting infection in our body. So decrease in blood cell counts will cause opportunistic infections to take hold. They will get sick easily, okay? It's kind of like people who have AIDS, right? Acquired immunodeficiency syndrome, right? Immunodeficiency syndrome, they have less of an ability to fight off infection because of decreased blood counts, right? Because their problem is damage. Same thing like leukemia, right? It's damage to the immune system. This is damage to the blood cell counts, red and white cells, so we worry about anemia and opportunistic infection. At 500 millisieverts, we begin to lose half of the lymphocytes in our body. Okay, lymphocytes are a type of immune defense cell, part of our lymphatic system, and they do the job of also fighting infection. And at 500 millisieverts, to double the threshold dose for decreased blood counts, you get 50% loss of lymphocytes. Here's an important thing to remember: if I give you 500 millisieverts, you've reached the threshold for lymphocyte loss, okay? But you have also passed the threshold for blood cell count decrease, right? Both things are now going to happen, okay? It adds up. Once you pass one threshold, you get that thing happening. You pass the next threshold, both of the previous things now happen, okay? You get so it builds up, right? If you give someone 1,000 millisieverts or 1 sievert, they could die. But before that, they're going to lose half of their lymphocytes and decreases in blood cell counts too. Both of those things are going to happen on top of the fact that they're now at risk for death. Okay, they could have already been at risk for death because of the loss of these things. They could get an infection and die from a cold.
1,000 millisieverts.
One
is
sievert.
1 gray.
1 gray in X-rays. If this is 1 sievert of alpha, it's not 1 gray of alpha. But if it's X-rays, yeah, it's 1-to-1 relationship with X-rays. You're thinking the right things. 3.5 to 4 sieverts is the LD5030 for humans. LD stands for lethal dose. 50-30 says 50% of the population within 30 days. So 3.5 to 4 sieverts is lethal to people. Half of them will die within 30 days. It talks about an exposure to a population. But anyways, roughly speaking, you have a 50% chance of dying within 30 days if you get 3.5 to 4 sieverts, right? So you can die above 1 sievert, but you have a 50% chance of dying above 3.5 to 4 sieverts. Makes sense? Your probability of death now goes up a lot. 6 to 7 sieverts is the LD100. All the people die. Nobody survives that. Okay? It's just statistically, everyone will not survive 6 to 7 sieverts. Now, it's really hard to do this, right? You have to really, really try to give somebody that much radiation. Even in the highest radiation environments we have in our hospital settings, you really can't get to these levels. There's going to be all kinds of alarms and bells and whistles and all this stuff. You're going to see other bad things happening to the person before this, right? But it can happen. It can happen in radiation accidents, okay? Such as what has happened in places like Chernobyl, right? The people died from radiation exposure because they received like hundreds of times this amount, and they died within hours, some of them. These next are what are called partial body effects. Okay, so exposure to only a piece of the body. At only 50 millisieverts, we can start to see chromosome aberrations. These were what I showed you on the karyotype as being damage to the chromosomes, visible damage to the chromosomes. That can happen at actually really low levels, 50 millisieverts. 2 sieverts, so you collimate to like an area, and you're going to do a radiation therapy on somebody, and the area you collimate to, if you give them more than 2 sieverts in that area during that time, you can cause a sunburn. Erythema is a reddening of the skin or sunburn. Add on 1 more sievert, and now they'll lose all the hair in that area. Epilation. If you give them 3 sieverts, they will have chromosome aberrations, erythema, and they will have lost their hair in that area. This is not like chemotherapy hair loss where it's whole body. They will only lose the hair in the area that they were exposed. This is an example of a skin burn from radiation therapy. And you can see how bad it gets, right? It really is, it's a burn, right? It is burnt the tissue. Basically it heats up the tissue so much that it does it just like a burn. It can be just like a full thickness 3rd degree burn, okay? Serious skin burns to patients are reported in even modern times for cardiovascular, interventional, and C-arm procedures. Part of it is the high exposure. The other part of it is the proximity. They're very close. Like in angiographic procedures, the beam has to be very close to the body to achieve great detail. So they're using high amounts of radiation very close to the body. Okay, so it's not, outside of the realm of possibility. These things can happen. So radiographers who work in these settings have to be, extra in tune to how much they're using, making sure they're not passing certain threshold doses. And if they are passing certain threshold doses, they better have really good reasons to do it. These are gonadal effects, gonadal early effects. 100 millisieverts to the gonads in a male causes decreased sperm count after a few weeks. Let's pause for a second. Why might it cause sperm counts to drop after a few weeks, but not immediately? What do you think, Abby?
It takes a while for sperm to mature.
Right. So at any given time, the male already has mature sperm, right? So for several weeks, they have a bank, really, of mature sperm, right? Already produced mature sperm. But those immature sperm that were part of the gonads, those were the ones that had the effect. Those were the ones that were sensitive to the radiation. Remember, we talked about cell sensitivity, and the more specialized a cell is, the more radio-resistant it is. Well, mature sperm, spermatozoa, are very radio-resistant, so they don't get harmed. Okay, but the spermatogonia, and also the stem cells that those are coming from, those are easy to harm. So they make sperm right now. That sperm's ready to go. The sperm that is being produced, that will be harmed, and that will not be able to do its sperm stuff. Okay, so they test them after a few weeks, and sperm counts are decreased because the sperm did not generate. 100 millisieverts to the female can suppress menstruation. The ovulation cycle won't happen. The ova, the follicle from which the ovum comes, will not generate. So there won't be growth of the ovarian follicle, no ovulation, therefore no menstrual period. There's no preparation for pregnancy, so no menstrual period after. No kids, but this is temporary. Importantly, this is all temporary. Good. So 2 sieverts. Temporary infertility. So this is just damage, right? 2 sieverts gives you temporary infertility. So, that's 20 times more than these first doses. 5 sieverts to the gonads, permanent sterility. Okay, the males and females will no longer be able to produce genetic cells any longer at 5 sieverts or higher. Delivered to the whole body, though, it's a 50% chance of death, right? So that's a lot of radiation, right? But delivered just to the gonads, permanent sterility. If that were delivered to the whole body, the person has a 50% chance of dying. Coin flip, chance of dying. Okay. Let's make some other notes. The lowest radiation dose resulting in any noticeable, measurable biologic effect is 50 millisieverts. That's the one that caused visible chromosome changes. Such a dose can be an acute one-time exposure, not protracted or fractionated. That would need to come all at once in order to cause that threshold, in order to pass that threshold. So when we're talking about these doses, we're talking about single exposure doses to cause these effects, right? 5 sieverts would cause permanent sterility, but only if you did it all at once, right? If I spread it out over a whole year, it's not going to cause sterility. Okay, so all at once, though, can do that. And then a minor note to compare this to some previous stuff we learned. 500 millisievert exposure is the dose equivalent limit for a one-time life-threatening emergency exposure. This is not really used for us. This is used for like rescue workers and stuff who have to go into, a power plant melts down. This is their lifetime limit. So if a rescue worker goes in, saves some people, but also gets, that amount of radiation during that time, they can never ever do that again. Okay, that's a one-time limit. Because it's damaging, right? 500 millisieverts can cause big harm to the body. That's 10 times more than the number that causes visible chromosome changes. We also have to consider this, because I've been thinking about this recently with the Artemis missions to the moon. We have to consider this a lot with the royal we of science has to consider this a lot with the astronauts, right? When they're up there above Earth's atmosphere, they don't have the protection from radiation like we do. They're constantly getting exposed to cosmic rays, and so they have to design the design this stuff into their suits that they wear, into their habitats that they live in, their spaceships, things like that. And one interesting way, so how do we reduce radiation exposure? What are the 3 things we can do to minimize exposure to radiation? Cardinal rules of radiation safety: shielding, distance. Collimating helps, but time is what I'm looking for. Time, distance, shielding, right? So the astronauts, they only go up there for a certain amount of time. Distance is not a factor because they can't get away from the radiation, okay? So they have a certain amount of time they're up there. They can't get away from the radiation, so all that they can do is maximize shielding, right? Their spaceships have to be able to get into space, so they can't be made of lead, right? So they have to be smart about this, right? So one way they've done this is they have figured out that water is a fantastic shield. So there's ideas to basically make the water storage tanks basically a sheet-like blanket type tank that wraps around the spaceship and is part of the walls of the spaceship to act as a shield for them. They still can't get around it though. They're getting exposure, and they're getting so much exposure up there that they really have to consider real effects to the body after they come back to Earth, the chances of cancer, things like that. So they're taking real measures. I mean, on top of like just getting and on top strapping yourself to a rocket ship and flying up there, they're getting real measurable changes, real measurable risk by being up above Earth's atmosphere and constant radiation exposure. So anyways, so it's not just radiographers, right? It's not just nuclear workers. It's other people too that have to consider these type of things. Okay. Next, I just want to keep on chugging through this. Next are lethal doses. Lethal doses always are called the LD something, okay? Like the LD 5030 or the LD 100. The LD lethal dose is expressed with a fraction to the side of it. X and Y are given as the variables here. X is the percentage of the population that would die from the exposure. Y is the number of days over which this would be measured. The LD 5030 for monkeys is 4 sieverts. It's pretty much the same for us because we're just, hairless monkeys. And it's different for different animals. By the way, saying that 50% of a population will die from 4 sieverts is the same thing as saying that if I give you 4 sieverts, you have a 50% chance of dying, right? Saying half the people will die is the same thing as saying one person has a 50% chance, a coin flip chance of dying. Okay. So this is the LD 5030 for different animals. We're in the 3.5 to 4 gray range. So are monkeys, primates, or just fancy primates. Rats and mice, 9 gray. Look at how unfair this is. Goldfish and insects, 20 gray and more than 20 gray for insects. It has to do with specialization. The more specialized the organisms are, the more tightly they fit into their little ecological niche, but the more specialized they are. That's the important thing. For some reason, goldfish, and for some reason, insects. This is why you hear about like cockroaches being able to survive like a nuclear blast. By the way, cockroaches cannot survive the blast. They can survive the radiation after the thing has happened. You can blow up a cockroach with, just like you could a person, right? But they can survive the radiation exposure because they are very resistant. It takes more than 20 grays to kill insects, to even give insects a 50% chance of death. So they're really resistant to radiation. Here's an interesting fact. The highest measured dose a human has ever survived is 8.5 gray, which is above the lethal dose for all people. Okay, so someone somewhere survived an exposure that should have killed them. Okay, and you can look this up. It's either Chernobyl or Hiroshima, Nagasaki. Those are the only incidents that gave that much exposure to people that we've been able to measure. So it's one of those 2 incidents. I bet you it was Hiroshima, Nagasaki. But you can go look it up if you want. The LD 160 is 7 gray when medical treatment's available. Medical treatment's going to be a big part of this, okay? Without medical treatment, it's lower. It's only about 6 gray without medical treatment. Medical treatment allows us to stay hydrated and continue to be given nutrients without relying on our gastrointestinal system to function. If our GI system doesn't function, you can only survive about 3 days without water, right? And so one of the first things that happens to the whole body after high doses of radiation is what's called gastrointestinal syndrome, in which we are no longer able to absorb water or nutrients through our GI tract. And so if you can't pipe it in some other way, the person is more likely to die from that. So here's your LDs for, these are all humans, but this is you had the LD 50-30, half of the people within 30 days, so 50% chance of death, 3.5 to 4 gray. Without medical treatment, 6 grays should kill everybody. With medical treatment, 7 grays is about that number. And no one's dying under 1 gray. This response curve plots it out for you. So if you look down here, dose is horizontal, lethality is vertical. Up at 6 grays, all of the people, right? So 100% of people are dying at 6 grays. Go to 3.5 gray, follow it up till it meets the plotted line, and you have 50% lethality, 50% chance of death. And then you go down to 1 gray, and that's the threshold. The graph goes to a toe at the threshold. It goes to 0. So no one's dying under 1 gray, 50% chance of lethality at 3.5 gray, 100% chance of lethality above 6 gray, assuming no medical treatment. Alrighty, we're doing good. I think I might actually get done with this, which is fantastic. Okay, so remember, we're talking about early effects that do not happen in the X-ray room, but can happen in principle to from high level acute doses of radiation, such as what we've been describing. At these high levels, above 1 gray, we have to be concerned for something called acute radiation syndrome. So once you pass the 1 gray threshold to the whole body, now the organism has a chance of death, okay? Their chance of death increases with an increasing dose and no medical treatment, and they're going to develop several different syndromes as the dose that we're talking about increases. The first thing to do is discuss what happens if you get like a lot of radiation, but you don't reach the threshold for death. So this is the area between 0 and 1 gray, but really it's between about a half gray to 1 gray, 500 millisieverts to 1,000 millisieverts. This is when we start to see some interesting things happening. Humans subjected to high amounts of radiation, not exceeding 1 gray, may experience symptoms of nausea, vomiting, and diarrhea, accompanied by a general feeling of malaise or weakness. It's kind of like a really bad flu. These symptoms will subside after a few days with no further somatic complications for the individual. This is pre-radiation syndrome. This is before acute radiation syndrome. These are levels below 1 gray. This is not radiation syndrome. This is not life-threatening. It's not fun, you know. It's going to cause chromosome changes. It's going to cause, potential blood cell suppressions, right? We learned about all that. So some things are going to happen to the body, but importantly, it's not lethal. It is sublethal at these levels. Now, acute radiation syndrome is life-threatening by definition, and so it requires at least 1 gray. So what we'll be talking about here forward will include, remember, these add up. So if you get to 1 gray, they're going to develop acute radiation syndrome, but you've already gotten past the 0 to 1 gray range, which means they're already going to be developing nausea, vomiting, diarrhea syndrome as well. Okay, so these add up. These effects all stack up. If you give somebody 1/2 to 1 gray, they get nausea, vomiting, diarrhea syndrome. You give them above 1 gray, they develop the acute radiation syndromes, but also they have nausea, vomiting, and diarrhea. Okay, so we don't skip things. We just keep adding. Let me briefly describe the stages of the syndromes first, and then we'll describe the syndromes themselves. Acute radiation syndromes have 4 stages called prodromal, latent, manifest illness, and then death or recovery. how long these stages last is inversely proportional to the dose, which means that as the doses get higher, these stages get shorter. Okay? Large doses of radiation make for very short periods between stages. We'll describe these stages in a moment here. They're a lot like the stages of any illness, though, right? You start to get sick, you feel a little better, then you get really sick, and then you get better, or you die, right? So it's similar in idea to any acute illness. All right, so let's go ahead and run through these. Acute radiation syndromes, or ARS, as I'm going to continue to refer to it as. Prodrome and latent stages. Doses above 1 gray is what we're talking about. Whole body above 1 gray. You're going to get nausea, vomiting, diarrhea syndrome because you passed the NVD syndrome threshold. We're going to get fever and faintness during the prodromal stage, which lasts from hours to days. Higher levels of exposure means it's going to last for shorter amounts of time. Sounds good, it's worse. You want it to last for long periods of time. Low levels of exposure last for longer. That's prodrome. So it's like feeling a little sick. Like, I got the exposure, something's not quite right. Okay? A little nausea, vomiting, diarrhea, a little bit of faintness, you don't feel so well, prodrome. And then these symptoms subside. The patient feels a false sense of recovery for a short period of time. This is called the latent stage. It's because all the damage happened, and now it's all building up now to the big event. Again, the bigger the dose, the shorter these stages are. Manifest illness is when the illness manifests, right? It's when you get sick, when you get really sick and have all the symptoms. After the latent period, prodromal symptoms return. They're worse this time, okay? Along with additional life-threatening symptoms characteristic of the subsyndromes described. We have 3 subsyndromes we're going to look at. This is manifest illness. Manifest illness can last from hours to months. High doses, shorter. Low doses, longer. And then what's going to happen after manifest illness is the person either gets better and recovers, or they do not, which is death. So death or recovery. Okay, so remember, we're above 1 gray here, so we're already into the life-threatening range. Above this life-threatening range, we have 3 increasing levels of severity. From least bad to worst, they go like this. So the least bad thing is hematopoietic syndrome, or hematologic syndrome. This deals with blood cell formation. Followed by gastrointestinal syndrome. As doses increase, gastrointestinal syndrome. Followed by the worst one, central nervous system syndrome. You guys have learned, hopefully by this point, when we talked about cell sensitivity, that nerve cells are very radio-resistant. They're hard to hurt, right? If we're giving enough radiation to hurt the nerve system, then it's very, very likely to cause death at this point. Okay, so we'll get there. We'll build up to it. The term hematopoiesis is a term meaning blood cell formation. Hematopoietic syndrome, or bone marrow syndrome, or hematologic syndrome, again, above 1 gray, the risk of death is damage to bone marrow. Bone marrow produces blood cells. Blood cells do things like carry oxygen, fight infection. Severe depression of blood cells results in anemia, causing hemorrhaging, and suppression of white cells puts you at risk for serious infection. The immediate cause of death from this syndrome, because remember, we're above 1 gray, so they can die. The immediate cause of death is likely to be from infection. The threshold for hematopoietic syndrome is 1 gray. Above 1 gray, this begins to happen. Once we get to about 6 gray, GI syndrome can happen. What is 6 gray? Why is 6 gray significant?
Above the threshold
It's above a threshold for what?
for, like, the human body.
death, right,
Yeah.
to half the people or all the people?
100%.
All the people, right? This is the LD100. So 6 gray and higher puts you at risk for GI syndrome, but you're already very likely to die. Okay, remember, we were already above 1 gray just getting to the hematopoietic syndrome, okay? So here, you get to survive only if you can receive medical care. Okay, and that only lasts up to 7 gray. Above 7 gray, medical care can do nothing for you. Okay, but 6 gray to 7 gray, GI syndrome can happen and we can save you. Okay, if you don't have medical care, we can't help you. But so here's the problem here: the risk of death is damage to the small intestine. What's the small intestine's job?
To absorb nutrients.
It's the absorber, right? Your stomach is the breakdowner, right? Your small intestine is the absorber, and your colon is the storer, right? The storage reservoir, right? Small intestine does the absorbing, right? If you have damaged small intestine, you cannot absorb anymore, okay? Your GI system does not work. Irreparable disquamination of the GI lining resulting in very poor absorption of water and nutrients. Disquamination is a term meaning flattening of the GI lining. Okay, the GI lining relies on the fact that it's got all these little finger-like projections called villi that increase the surface area inside of it. Think about the lumen of the small intestine. It's got all these little finger-like microscopic villi. Those are all flattened in GI syndrome. All the cells die, and the villi get flattened. You can no longer absorb nutrients, and most importantly, that's the first word in the second statement, it is irreparable. They're not going to get better. Okay, the GI lining is done now. Okay, it's not going to be fixable. They will not die if we can keep them hydrated and nutriized, right? Keep giving them nutrients, yeah? They will die, though, if we can't, right? 3 days without food, 3 days without water, 3 weeks without food, okay? If you keep them hydrated, but don't feed them, they've only got a few weeks, okay? You can't feed them through their mouth. You have to feed them through intravenous therapy now. They cannot absorb anything through their gastrointestinal system ever again. Okay, it is damage done, not repairable. The immediate cause of death is likely to be dehydration in these cases. 3 days without water, right? Maybe less in different circumstances. Electrolyte imbalance due to dehydration. So you get erratic, sporadic nerve signals because of electrolyte imbalance. We need like you've probably had times when you've gotten a cramp, right? That was an electrolyte imbalance, right? So now you got cramps in the whole body, even the heart, okay? So electrolyte imbalance. After that, even if you can solve that, you worry about malnutrition due to starvation. And then you also still have to worry because you already passed the hematopoietic syndrome too. So now they have all of this happening, plus they're at huge risk for severe infection because they're anemic and they're low in leukocyte count. So they're bleeding out, they're low in leukocyte count, and their gastrointestinal system is destroyed, okay? This is why the risk of death is so high now, okay? Above 6 gray to 7 gray, we can treat them with medical care, we can keep them alive, even though their GI system is toast. Central nervous system syndrome, happening above, you like this, happening above 50 gray, okay? So now we're well into the everyone's gonna die category, okay? The risk of death is primarily from acute damage to the brain. But interestingly, the neurons, the nerve cells, are so radio resistant that the risk of death is not that the neurons are getting destroyed. The risk of death is from intracranial hemorrhaging. You have so many cells and tissues bursting their membranes that you have blood vessels rupturing now, okay? Blood vessels rupturing creates intracranial pressure, stops the oxygenated blood from reaching the important parts of the brain. There's pressure, lack of oxygen, and they die from that. Okay. And again, remember the law of Bergoni and Trabando says the brain cells themselves are very radio resistant. They're not the thing that's being harmed here. It's everything that's supporting them. Their entire support system is failing them now. Here are the average survival times for these 3 syndromes. Hematopoietic syndrome above 1 gray has a survival range of 2 to 8 weeks. On average, people survive 2 to 8 weeks after this type of exposure. It's the infections that are getting them. Weeks of infection, opportunistic infection buildup. Now, their blood cells will repopulate eventually. You damage the bone marrow, but more bone marrow can be created. So if they can stay alive and healthy long enough, right? If we can keep them from getting sick long enough, this person will recover. At for the GI syndrome, 4 to 10 days. This is roughly the 3 days without water thing that I was telling you guys, and 3 weeks without food. A human can only survive, as they say, 7 to 10 days without nutrients, 4 to 7 days without water. Okay? So GI syndrome death in 4 to 10 days. Central nervous system damage, 2 to 3 days. Acute brain pressure can induce coma within hours, but we can keep them alive for potentially days. It's not repairable, but they can be kept alive long enough to, say bye to them and stuff like that. They're in a coma, though. That's the thing, is that within hours they're in a coma. Okay, so those are your 3 acute radiation syndromes. Let me show you a couple other things. For example, here is the GI lining of an animal, a rat. This is nice, thick, small intestine lining, okay, in A. Down at the bottom shows you the small intestine lining after 2 grays were given to the rat, okay? So this rat died. That's why we can see its body, because they autopsied it. But yeah, so you see how flattened it is, right? This same thing happens to people above 6 gray. Here's your thresholds if you weren't catching them as I was saying them. Hematopoietic syndrome above 1 gray, GI syndrome above 6 gray, central nervous system syndrome 50 gray is our threshold. Okay. Okay, early effects that are not lethal. Okay, so these are some other early effects. We've covered all the lethal stuff for today. Local tissue damage from radiation can cause organs to atrophy in size and decline in function. And remember, atrophy is lack of growth, right? Shrinking. Decrease in function, atrophy. Erythema is one of the possible effects. We learned 2 sieverts causes erythema, reddening of the skin, usually from radiation therapy. At high doses, a second wave of erythema follows the first wave, followed by disquamination of the skin. The skin begins to ulcerate and die and sloughs off. 2 grays for that threshold dose. An epilation, hair loss due to radiation exposure, threshold is 3 gray. So that gets me done with my notes for today. What we'll do